solve some systems of nonlinear equations. For the purposes of this video, I'm going to assume that you already know the strategies of graphing, substitution, and elimination when you're solving linear systems. So now let's jump in and use those same strategies to solve nonlinear systems. And let's start with this one. And notice that we have y equals x squared. There's our nonlinear equation. And this one is linear, but we would consider this a nonlinear system. Remember, the goal when solving the system is to find all ordered pairs that would be solutions to both or all of the equations in the system. So this one, we're going to solve by graphing, because graphing shows you a picture of the solutions. So let me bring in this grid right here, and let's just graph y equals x squared. We know that's a parabola that goes through the origin, or has a vertex at the origin. Let's just plot a few points so we have a nice graph. It goes through 1, 1, and let's see, 2, 4, negative 1, 1, and negative 2, 4. That might be enough for us to have a respectable graph. Let's see how well I can do here. Missed it a little bit right there. And missed it a lot right here. But there's my picture. I hope you can envision it going a little bit better through those points. So this is a picture of the solutions for this equation. So every point on the parabola is a solution to the equation, and every solution to the equation lies on that parabola. Now we graph y equals x plus 2. We just have a linear equation. Notice those y-intercept is 2, the slope is 1. So I can graph that relatively easily. Whoop, I didn't grab my straight edge, so I'm going to do this freehand. And we have that picture. Now when we look at the solutions right here, the point where they intersect is at this point 2, 4. And we have another solution right here at negative 1, 1. So as is sometimes the case with a nonlinear system, you'll have more than one solution, right? Or could have. So the solution to this system is this set of points, this set of points that are negative 1, 1 and 2, 4. And you can double check. You could pop those two ordered pairs into both equations, and you would see they would make them both true. Let's look at a very similar equation that gets a different result. I just changed the linear equation. Let's look at this. Y equals x squared and y equals x minus 2. Now instead of the y-intercept being positive 2, it's negative 2. And I have already taken the time to do the graphing. And notice what you see here, that they don't intersect at all. So we would say that there is no solution to this problem. And let me just mention this. When we're looking at the graphs and implied by the directions of all the problems we're doing today, we're assuming that we're looking for real solutions. It turns out that there are some non-real solutions, meaning there are some solutions that have eyes in them, but we aren't looking for those today. So we would just say there's no solution to this system. Let's solve another one. And I'm going to move away this title because I think we're going to need more space for some of these systems. So here's the next system. We could solve this one by graphing, but let's not. With the directions say solve using substitution. Remember, for substitution, we're going to solve for either x or y in one of the equations and substitute it into the other equation. So I like that for the second equation. I'm going to solve for x. It doesn't matter. Remember, you could solve for y, but I'm going to just solve for x. So I have x minus y equals 1. So if I add y, I have x equals y plus 1. Remember, with the substitution strategy, we substitute that expression into the other equation. So we're making that substitution for x. Let me be clear. This is going right in here for x in the first equation. So we have y plus 1 squared plus y squared equals 25. And we have a quadratic equation that we're now solving. So let's square this binomial. We have y squared plus 2y plus 1. And then we have plus y squared equals 25. Let's set this quadratic equation equal to 0. And as I do that, I'm going to combine these like terms. So I have 1y squared plus 1y squared. That is 2y squared plus 2y. I have this 1. I'm subtracting 25 from both sides. So I'd have minus 24 equals 0. So I have this quadratic equation to solve. I notice there's a common factor of 2, so I could factor out the 2. I'm just going to choose to divide both sides by 2, so I don't have to look at that 2 any longer. So if I divide both sides by 2, I have y squared plus y minus 12 equals 0. Factor. So I have y and y. Let's see, 12 would break down into a 4 and a 3. That would give us that positive 1 in the middle. If we have a plus on the 4 and a minus on the 3. So our y values equal negative 4 and positive 3. Now my job is to find the x coordinates that go with them. And here's one way in which this is different from solving a system of linear equations. When you're solving linear equations, it doesn't matter what equation you substitute your value in to find the x coordinate. But here it does. And let me show you why in just a minute. I'm going to substitute negative 4 into the linear equation. In fact, I'm going to substitute it into this version of the linear equation. So I'm coming up here, and we have y equals negative 4. And if I make this substitution, I would have x equals negative 4 plus 1. So x equals negative 3. So the ordered pair is negative 3, negative 4. And I have the y value of 3. Let's substitute it in as well. So we have x equals 3 plus 1, or x equals 4. So our ordered pair is 4, 3. So the solutions to this system are these two ordered pairs, negative 3, negative 4, and 4, 3. Now let me just point this out. I did graph these two equations. Remember, x squared plus y squared equals 25 is a circle centered at the origin with a radius 5. Here it is. X minus y equals 1 is a linear equation, and I graphed it as well. And I just wanted to point out that we do get the same solutions. This point 4, 3, and this point negative 3, negative 4. Now let me talk about this for a moment. The fact is that we substituted negative 4 into this linear equation. What if we had substituted negative 4 into the first equation? So let's come back here and substitute y equals negative 4 into the first equation. So we have x squared plus negative 4 squared equals 25. We get x squared plus 16 equals 25. We get x squared equals 9. And that generates x equals plus or minus 3. So in fact, this would represent two ordered pairs, 3, negative 4, and negative 3, negative 4. And you can see why if I bring you back to the graph. When we substitute negative 4 into the equation that represents the circle, you'll find every point on the circle that has a y value of negative 4. Let me come back over here for you. Here's our circle. Here's our y value equaling -4. Ooh, the y value also equals -4 right here. But that is not, yeah, -4 right here, but that is not a solution to the system. So I would substitute my values into the equation of lower degree so that we don't have this scenario happening. We don't get a solution that doesn't in fact work. So when I'm looking to make a substitution, I have my y values. I know I need x. I see one equation is second degree with respect to x and one is first degree. Substitute back into the equation of lower degree so that you don't get any of those extraneous solutions that don't work in the system. Let's solve another system. We're going to solve this one using the elimination method. Now, let me point out that substitution would work just fine. You could solve for x in the second equation and substitute it in here, or solve for y here and substitute into the second equation. That would be totally fine. But let's practice the elimination method. I see that x is second degree here and first degree here, so I can't eliminate those x's easily, but I can eliminate the y's. Notice this is a -3y. All I need to do is make sure this becomes a +3y. So I'm going to multiply the first equation by 3. So my system becomes 3x squared plus 3y equals 21, and x minus 3y equals 9. And as we expect with the elimination method, and you could be using a book where they call it the addition method, those are one and the same. When I use that method, when I add, one of the variables will be eliminated, in this case the y's. So when I combine these, notice they are not like terms, so I can't write it as one term, so I just write their sum. I have 3x squared plus x on the left. The y term is eliminated, and on the right-hand side, I have 30. Now I have a quadratic equation to solve, so let's set it equal to 0. Oop, that's squared. I'm going to try factoring. If factoring doesn't work, I can use the quadratic formula, but I'm going to try factoring first. So I have 3x and x, and I roll through the possibilities for 30. You have 1 and 30, 2 and 15, 3 and 10, 5 and 6, in either order. I'll let you test those, but ultimately you will find that 10 here and 3 here will give us that +1 that we need in the middle if we put a plus on the 10 and a minus on the 3. So we continue to solve, we would get x equals -10/3 and x equals +3. So we have the x coordinates for the solutions for this system. Now, I know my value for x. I'm trying to find the values for y that go with them. Notice with respect to y, both of these are first degree. So for this one, it doesn't matter which equation you substitute it into. I'm going to substitute it into the, let's substitute it into the second equation anyway. So I'm going to substitute in x equals -10/3 into this equation. So I have -10/3 minus 3y equals 9. You could just add 10/3 to both sides, or you can clear out the fractions. I think I'll do that. I'm going to multiply by 3. So I have -10 minus 9y equals 27. Add 10. And divide by -9. So one of the solutions to this system is the ordered pair -10/3, -37/9. And for the other solution, let's substitute x equals 3 into the equation. We have x minus, whoops, there's the 3 going in right there. 3 minus 3y equals 9. And we solve that linear equation. So we have 3, negative 2. So let me write it very clearly here. The solutions to this system right down here are negative 10 thirds, negative 37 ninths, and 3, negative 2. And if you wanted, you could check this by looking at a graph, see if they seemed about right. Notice that this one would be a parabola, this would be a line, and having two solutions isn't unexpected if you have a parabola and a line. Let's look at another system. The directions are solved this time. And we're going to solve by using substitution or elimination, whichever seems appropriate in the next few problems. Now, elimination doesn't seem reasonable because I don't have a y squared here and I have a y squared there. Similarly, I don't have an x squared up here. I wouldn't be able to eliminate anything. So it looks like substitution. So I'm going to solve for x or y in the first equation and substitute it into the second one. So I have xy equals 12. Let's just solve for y this time. So I divide by x. And so my substitution is going right in for y in the second equation. So I have 3x squared minus 12 over x squared equals negative 24. Let's keep solving. I'm going to square the 12 over x. So when I do that, I have 3x squared minus 144 over x squared equals negative 24. Now this is an entertaining equation to solve. Let's multiply both sides by x squared to eliminate that denominator. So I'll have 3x to the 4th minus 144 equals negative 24x squared. So let me write this in case you didn't see what was happening here. I was multiplying both sides of the equation by x squared. But now we have a 4th degree equation. Let's set it equal to 0. So we have 3x to the 4th plus 24x squared minus 144 equals 0. Now I do notice there's a common factor of 3, so I'd like to divide by that 3, so my numbers will be smaller. So if I divide both sides of the equation by 3, I'll get x to the 4th plus 8x squared. Let's see, 144 divided by 3 is 48, so minus 48 equals 0. Now this isn't quadratic, but it's quadratic in form, so it kind of acts like a quadratic equation. We can solve it by factoring. So we have an x squared and an x squared here for 48. 6 times 8, no, that's not it. How about 12 times 4? 12 times 4 would work if we put a 12 here and a 4 here with a plus on the 12 and a minus on the 4. Let me slide it up just a little bit. Actually, let me come up here so I don't run out of space. Let's put x squared plus 12 times x squared minus 4 equals 0. Just moving this equation up here. Now, when we solve this, we know that means x squared equals negative 12 and x squared equals positive 4. Now, notice this one, if we were to solve for x, we would get non-real solutions. So there's no real solution that is generated from this equation. So let's move on to this one. We have x equals plus or minus 2. So we do have two x coordinates. x equals 2 and x equals negative 2 for this particular system. So we're going to try to find the y values that go with them. Let's start with the positive 2. I'm looking back over here to decide which one to substitute it into. Besides the fact that this one looks easier to me, I know I'm solving for y, and with respect to y, this is first degree and this is second degree. So I want the equation of lower degree, right? If we are only looking at the y's. So again, first power here, second power here, I'm substituting it into this first equation. So I have 2y equals 12 or y equals 6. So my solution is 2, 6. And similarly, we substitute in negative 2. Negative 2. And we get negative 6. So let me be very clear down here. The solutions to this system are negative 2, negative 6, and positive 2, positive 6. I'm not going to take the time to graph them, but I will just mention that each of these are hyperbolas, and we now know that they would intersect at those 2 points. Let's solve another system. Let's let it be this one. Now my choice is substitution or elimination. Those are the strategies that we're practicing right now. I'm going to use elimination, but I do want to mention one thing before we continue. If you were going to use the substitution method, you don't actually have to substitute for x or y. You could substitute for x squared or y squared. For example, I'm just going to bring this here. If you were going to use the substitution method and you had x squared minus 6y squared equals negative 5, and you solved for x squared, and you had this, you could make the substitution for x squared right here. I just want to point out that that is a possibility. I'm not going to choose to do that, but you certainly could. I'm going to use the elimination method on this one, I think. It looks like it would work pretty nicely for this one. So we can either eliminate the x's or the y's. I think I'll multiply this first equation by negative 2, and that will eliminate my x's. So here we go. We're going to multiply by negative 2 here, and my system becomes this. Negative 2x squared plus 12y squared equals 10. And I still have 2x squared minus y squared equals 12. So when I add the equations together, I have 11y squared equals 22. A nice little quadratic equation to solve there. So I have y squared equals 2. So I get y equals plus or minus the square root of 2. So now we need to find the x coordinates that go with each of those y coordinates. So let's start with y equals the positive square root of 2. So I'm solving for x. Notice with respect to x, it's second degree and second degree. So you can choose either one you like to solve for x. So if I'm solving for x, I might as well use this first equation. So I have x squared minus 6 times the square root of 2 squared equals negative 5. Let's see, that's x squared minus 6 times 2. Square root of 2 squared is just 2. So we have x squared minus 12 equals negative 5, or x squared equals 7. So x equals plus or minus the square root of 7. So with this y coordinate, I have these two x coordinates. So I'm going to write that as positive square root of 7, square root of 2, and negative square root of 7, square root of 2. But that only takes care of the square root of 2. I haven't substituted it in negative square root of 2. Let's do the same thing. Y equals negative square root of 2. And I hope you can see that the algebra will be almost identical. Because when we square that negative square root of 2, we end up with a positive 2. And we have exactly the same equation as we had right here. So I'll go through this quickly. We'll get x squared equals 7. So again, we get x equals plus or minus the square root of 7. So with the negative square root of 2 as a y coordinate, again, I have two x coordinates. So we have square root of 2, negative square root of 2, and negative square root of 7, positive square root of 2. Let me caution you about this. Sometimes I see people write solutions that look like this, plus or minus the square root of 7 and plus or minus the square root of 2. I would recommend not doing that because this is very ambiguous. It's not clear to somebody reading it whether the positive square root of 7 only goes with the positive square root of 2, or is it all possible combinations of this expression and this expression. So I would not do that. I would list them as I did here. Let's write them. It's square root of 7, square root of 2, negative square root of 7, square root of 2, square root of 7, negative square root of 2, and I've lost one, haven't I? Oh, on this one, there should be a negative. Negative square root of 7, negative square root of 2. And then it's very clear what the solutions are for this particular system. Let's do one last problem. Let's solve this system. I'm looking to decide whether to use substitution or elimination, with us having a quadratic expression here with respect to x and with respect to y. Elimination doesn't look too good, so let's use substitution. We can easily solve for x or y in the first equation and make a substitution into the second equation. So let's do that. So we have x plus y plus 3 equals 0. If we solve for y, we'll have y equals negative x minus 3. When we make the substitution, we do need to make sure we substitute it into both places where you see that y. So it will go right here and right here as we make that substitution. So we have x squared plus negative x minus 3 squared plus 4 times negative x minus 3 minus 3x equals negative 3. We need to square this binomial. Now you can go to scratch paper and do it. But ultimately you would get x squared plus 6x plus 9, right? That's just squaring that binomial. Now let's distribute the positive 4. So we have negative 4x minus 12 minus 3x equals negative 3. We have some like terms to combine. Let's do that. We have an x squared plus an x squared. That's a 2x squared. 6x minus 4x minus 3x. That's negative 1x. 9 minus 12 is negative 3. And that equals negative 3. We have a quadratic equation. Let's just set that equal to 0. So we have 2x squared minus x equals 0. This one's factorable by just factoring out the x, and we would have 2x minus 1. So the x coordinates of our solutions will be 0 and notice from this factor, we would get x equals 1/2. So So our task now is to find the y values that go with these x values. So I'm trying to find y. Notice with respect to these two equations, the first one has y to the first power, the second one has y to the second power. We're going to substitute them into the equation of lower degree. So we're going to substitute the 0 into the first equation, or this equation right here, which is equivalent to that first equation. So let's do that. We have x equals 0. So we substitute it in. We have y equals negative, well, 0 minus 3. So we have y equals negative 3. So our solution is 0, negative 3. And we substitute in x equals 1/2. So we have y equals negative 1/2 minus 3. We need to do a little arithmetic there, get a common denominator, and we get y equals negative 7/2. So our solution is positive 1/2, negative 7/2. So the solution to this system is this pair of ordered pairs, 0, negative 3, and 1/2, negative 7/2. And I hope you have some fun solving some nonlinear systems.